All right, hello everyone. My name is Zachary Weiss, and my project is the improved electrosurgical device. So, a little bit of background. What is electrosurgery? As the name implies, it's basically just using electricity to cut biological tissue. Depending on the type of voltage, the frequency at which one is applying it, one can do everything from cutting to coagulating to desiccating to fulgurating to cauterizing tissue. As a result of this wide range of uses, or wide range of applications, you can see use in it for major tissue dissections, as well as surface level cuts. Specifically, our team is interested in solid organ dissection, as it has a high incidence rate of post-op complications with hemorrhaging in something like 20 to 40% of surgeries. So this project was commissioned by Dr. Omar Barakat of the Baylor College of Medicine. The driving concept behind this commissioned project is that there's a lot of multi-tool operations during electrosurgical operations. If we can simplify and integrate multiple of the functions and tools that surgeons need to interact with during these surgeries, we can hopefully reduce the rate of complications and reduce surgeon error. Our team consists of 4 undergraduates, myself, Benjamin, Celeste, and Elizabeth, our KHC mentor, Dr. Emily Haynes, our engineering mentors, Dr. William Hauser, Gutierrez, Wing, and Russo, and the medical doctor who's been advising us and is our client, Dr. Omar Barakat. Our project goal is to create an improved electrosurgical device that allows for minimal to no blood loss. And we're doing this by integrating a multitude of these different tool functions, namely integrating electrocautery and dissection by high voltage AC, an oscillating tip which assists with separating tissue from vessels, a saline drip which assists with irrigation and electroconductivity, and on-device controls preventing the need for averting one's eyes from the surgery or interacting with other off-surgical target devices. So the design process. We inherited this project from a team from the prior year. They primarily had focused on device conceptualization, defining a lot of benchmarks and specific requirements for deployment, as well as the general package design and some of the oscillatory design. Our primary additions this year were to focus on taking that concept in their initial work and turning it into a functional prototype. And the hope is that with the functional prototype we've created, next year that can be used in testing on actual tissue. So this year, the primary changes we made can be broken down into 5 categories, those being implementation of electrical connectivity, an update to the motor case and oscillatory design, the waterproofing of the case, the integration of onboard controls, and the integration of a saline drip. Starting with the electrical connectivity, the prior team sought to electrify the probe with a slip ring design. Unfortunately, this wouldn't be suitable with the kind of power that we're looking for, as well as the high speeds at which the probe will be oscillating. Slip rings are prone to wear over time, especially with the speed at which it would be being used, and simply can't carry the kind of current we need to work with. Some of those specs are listed on the 3rd bullet point. Our solution was instead to clamp a wire to the probe, pictured in the bottom picture, right near the pivot point, so the location that the probe rotates about. As such, we minimize the amount of motion that the connection to the probe actually experiences, and this increases the longevity of the connection and ensures good connectivity both initially, during oscillation, and 10 years down the road. We stress tested this for multiple days running at full speed. Luckily, it seemed to hold. We additionally had backup ideas in the event that this failed and showed poor connectivity or poor continuity. Luckily, we didn't have to resort to those, but we have those on deck in the event that once stepping this up to the actual operating voltage, we start seeing issues that would require a different solution. Onto the update of the motor case and oscillation design. So to meet the oscillatory specifications required, the prior team's motor wasn't really up to spec, couldn't move fast enough, wasn't able to output the proper amount of torque. We swapped this out for a medical grade motor that had an extremely high RPM, around 10,000 rotations per minute. Different torque specs, different sizing. Due to the changes in sizing, we had to modify, there were some rippling modifications throughout the overall design itself. What's pictured on the right-hand side of the slide is the offset key that goes onto the end of the motor. As you can see, it has a slight offset profile here. This is where the end of the probe goes into, and it causes the oscillation as the key itself rotates. So we had to redesign this key slightly to accept the different size of the motor, as well as the geometry changes around that. Similarly, we had to resize some of the geometry of the case. This led to a slightly better ergonomics as the diameter decreased, allowed for easier holding in the hand. And similarly, the changes in the weight balance made for a more natural pen-like feel compared to the previous rear-heavy kind of design that we inherited. And here is a quick video just showing how fast that rate of oscillation is with an early prototype of the medical grade motor. On to waterproofing. So to be able to use the device in a sanitary fashion in a medical environment, it needs to be able to resist splashes of blood and viscera and also allow for easy cleaning. Most importantly, you can't be allowing for bacteria or blood or viscera if you're getting into any small cracks or crevices or inside the device itself, as if so, it's going to harbor bacteria, it's going to allow it to grow, and it's no longer going to be sanitary. You can't clean it properly or easily. In an actual manufactured device, we'd likely be looking at an injection molded case, in which case you'd have a smooth exterior and no small crevices on the outside. Easy cleaning can be wiped down or treated with a gas type of sterilization. Unfortunately, all our prototyping at this point has been done by 3D printing, as that's what we've had access to during the pandemic. As a result, the first part of this approach to waterproofing was to seal the entire exterior in a 2-part epoxy resin. This filled in all the small crevices and cracks of a 3D printed device. And then secondarily, we focused on preventing water leakage through the actual pivot point where the probe exits the device and oscillates about. We did so by fixing a grommet pictured on the right. At this point, it's an interference fit grommet. And as such, even while you have the probe oscillating and perturbing the small pivot point, liquid isn't able to pass through. We stress tested this as well, submerging it for well over an hour in dyed liquid, and saw if any liquid would transfer into the inside of the device. Luckily, after over an hour, we saw no transfer of dye, and this met the specifications for waterproofing that we needed. On to the integration of saline drip and controls. So currently, we've acquired a saline bag and drip line from Tufts Medical Center, as we have a friend working there. We additionally have sourced an onboard PWM controller with an integrated potentiometer. This will allow for easy speed control of the oscillation, as well as complete cessation of any kind of oscillation, all from controls on the device. And currently, we're in the middle of revising the case and printing it out to fit in and the external drip line itself and the internal controller. With regards to future work, as mentioned earlier, due to learn from anywhere, we haven't been able to actually work with the voltages that one uses in actual electrocautery. The hope is that once back in person, the following team will be able to actually take that, take our updates to this design, test it initially on tissue from a meat market, liver, kidney, spleen, so on and so forth. Given good results there, they'd be able to move on to actual animal trials with Dr. Omar Barakat. And from there, we'd be moving on to, or the next team would be moving on to design for manufacturing, design for assembly, and regulatory compliance. Acknowledgements wise, want to thank all of my advisors, both engineering and KHC, my team members, as well as the entire KHC administration and community who made this possible. Thank you guys so much. And are there any questions I can answer?